We're going to be looking at understanding the labeling of orbitals and atoms using quantum numbers, being able to connect the shapes and names of the orbitals and their quantum numbers. Understand what the shapes of the orbitals represent in terms of electron probability, and be able to count the number of electrons that could fit in each orbital, subshell, and shell. All of this is trying to get comfortable with exactly the content of information about the electrons inside an atom, because that's going to be very important when we start looking at what possible reactions that atoms could have. Okay, so reminders from previous lectures. So matter on a small enough scale, i.e. like electrons, starts to behave like waves. There's only certain wavelengths and wave patterns that fit into a confined space. Otherwise, the waves cancel themselves out by interference. So only certain, once you got an electron that's attracted that closely to a nucleus, it's crammed in that space. It's sort of energetically bound there. And once it is, because of its quantum nature, there are only certain configurations of that wave that can fit around the atom. And the Schrodinger equation is the mathematical equation that tells us what the patterns are. We showed you the Schrodinger equation. We're not going to solve it, but we are going to look at the solutions. You know, that differential equation, what are the solutions it gives that tell you the spatial patterns? So at the atomic level, we know only about the probability where the particles are. Their exact location is not defined. When we look at these electron density distributions, it's not like it spends part of its time in one part of the atom and part of its time in the other. It's spread out throughout the entire atom. This is where the electron really is behaving like a wave. The wave function, it's a spatial function of x, y, and z that tells us where the electron's wave is most likely to be found. And also, when you plug it into Schrodinger's equation, it spits out what the energy of that wave is. But it's important to remember that it's the square of this, the square of the wave function, that gives the probability. We will not solve Schrodinger's equation, but we will spend a lot of time plotting the solutions. You can learn a lot about functions if you just graph them and understand the graphs, and that's what we'll be doing. We'll be graphing the solutions to Schrodinger's equation for Schrodinger's equation around a hydrogen atom in 3D space and understanding what they mean. Okay. So wave functions and quantum numbers. This is a bit of a repeat from last time, but it's important to put everything in context. So there's more than one solution to Schrodinger's equation. The solutions obey mostly straightforward rules. We'll actually see some of them this time. And in quantum mechanics, the mathematical solutions to the electron wave function, i.e. the orbitals around a hydrogen atom, can be classified into three sets of discrete numbers that give information about the region that the electron is likely to be in. And these numbers, as we talked about at the end of the last set of lectures, the principal quantum number, the label is N. The angular momentum quantum number, the label is L. Sometimes you'll see it more like a script L. And the magnetic quantum number, M sub L. So the principal quantum number gives information about the overall size and to large extent determines the energy. In fact, for hydrogen atoms, only the N determines the energy. The other two quantum numbers don't affect the energy at all. Angular momentum L involves the 3D orbital shape, and the magnetic quantum number, the orbital orientation about the X, Y, and Z axes. Okay, nomenclature you should know. The principal quantum number is the shell, the angular momentum is the subshell, and the magnetic quantum number is the orbital. So orbitals are the smallest classification, shell is the largest. And this is what we get. If we look at all the possible solutions up through n equals 4, when n equals 1, there is only one possible solution with angular momentum quantum number 0, magnetic quantum number 0, and this is the 1s orbital. There's only one orbital in the subshell, one orbital in the shell. For n equals 2, L can be 0 or 1, and M can be, if L is 0, M is 0. If L is 1, it goes from -1, 0 to -1. These are the 2s and 2p. Notice there is now one orbital in 2s and 3 orbitals in 3p. There are 4 total electrons. And you notice there's a lot of interesting patterns here that really come out just of the properties of the math. That there's 1 electron in the n equals 1, 4 in the n equals 2, 9 in the n equals 3. 16 orbitals in the n equals 4. I'm pretty sure you can guess how many orbitals are how many electrons are in the n equals 5 orbital. So that's as simple as that. Okay, and of course, p orbitals, there's 3 p orbitals, there's 5 d orbitals, and there's 7 f orbitals. But what I want to do, I think we should spend some more time looking at graphs of these functions, because that'll make it easier to memorize once we've got the visual pictures in our mind as